Hi, I'm Ryan Baker, and this is Big Day in Education. Today we're going to conclude Structure Discovery Week with a discussion of factor analysis. In factor analysis, you have a whole lot of variables, 100, 1,000, a million, and you want to group them into factors, which kind of are variables that express kind of the center of several variables. Now, factor analysis and clustering are not the same. Clustering finds how data points group together, and factor analysis finds how data features, variables, or items group together. So they're similar but orthogonal. In many cases, you can transform one problem into the other, but conceptually they're still not the same thing. Factor analysis can be used for several goals. For example, let's say you have a lot of quantitative variables. And since you have a lot of variables, you have high dimensionality. And you want to reduce the dimensionality into a smaller number of factors that you can then do analysis on. Now I should point out, by the way, and you saw that asterisk a second ago, factor analysis isn't just for quantitative data. Classical factor analysis, what people typically call factor analysis, is just for numbers, but there's also a variant for categorical and binary data called latent class factor analysis, and there's a variant for mixed data types called exponential family principal component analysis. And there are other variants as well. A second goal of factor analysis is, again, you have a lot of quantitative variables, and since you have a lot of variables, you have high dimensionality, and you want to understand the structure that unifies these variables. Much as in clustering, you might want to understand how different students group together and what the structure is between different students or different data points. So let's talk about a couple examples of how you might use factor analysis in educational data. The classic example, the one where factor analysis came from 90 years ago, is that you have a questionnaire with 100 items. And you want to say, do the 100 items group into a smaller number of factors? For example, you have a test with 100 items, and you want to say, are there actually kind of 6 topics on this test? Do the 100 items actually tap only 6 deeper constructs? Can the 100 items be divided into 6 scales? Which items fit poorly in their scales? Can we actually say of these 100 items we have 6 scales, but these 3 items really are not very good, we should probably get rid of them? This is common when we're trying to design questionnaires with scales and subscales. And since we use questionnaires in education a lot, it's a very relevant educational problem. Another example, and one that shows the versatility of factor analysis is, let's say you have a set of 600 features of student behavior, and you want to reduce the data space before running a classification algorithm. You could do fast correlation-based filtering, but here's an alternative. You say, do the 600 features group into a smaller number of factors? So, for example, the 600 features actually tap only 15 behavioral constructs in student behavior. And a third example, one that I've done a little bit of work along these lines, is let's say you have a taxonomy of 120 design features that an e-learning system, an e-learning lesson, could possess. You want to reduce the data space before studying the relationship between these features and student learning. So you say, do the 120 design features perhaps group into 8 factors? Or in other words, do the 120 features actually group into a set of 8 dimensions of tutor design, or 8 ways that designers kind of consider when they're building these tutor lessons? Whichever of these problems you're considering, there are 2 types of factor analysis you can consider. Experimental, which is where you determine the variable groupings in a bottom-up fashion. This is more the EDM way to do things. And confirmatory factor analysis, where you take some existing structure that some really smart person came up with, and you verify its goodness. And this approach is more common in psychometrics. Regardless of whether you're doing exploratory or confirmatory factor analysis, the mathematical assumption you'll usually see is that each variable loads onto every factor, but with different strengths. So in other words, it's not actually that there are these 7 variables that are in this factor, as much as that every variable is, but only 7 actually load strongly on it. Only 7 participate substantially in its calculation. Some strengths can even be infinitesimally small. So let's look at an example. Let's say that you've run factor analysis and you have your 12 variables and you have your 3 factors, and here's how much each one loads. Here's how much each variable loads on each factor. So, first question, can you write an equation for factor 1? Turns out to be pretty easy. You just take a straight up linear equation, like in linear regression. So, for example, what you'll get here for factor 1 is, look at the top left cell, 0.01 times V1 minus, go 1 down, 0.62 times V2, and go on down again, plus 0.003 times V3, and so on all the way through V12. You might want to pause here and take a look, and you'll see that every single thing in F1, whether the number is big or small, negative or positive, is going to end up being in this equation. So here's a pop-up quiz. Can you write an equation for F2? So which variables load strongly on F1? Well, what's a strong loading? What's actually a good number here? One common guideline that people use is that a strong loading is above 0.4 or below negative 0.4. Conry and Lee say, well, 0.7 is excellent, or negative 0.7, and 0.63 is very good, and 0.55 is good, and 0.45 is fair, and 0.32 is poor. This is one of these arbitrary things that people seem to take exceedingly seriously. You know, is 0.41 really just wonderfully strong and 0.39 is just junk? Another approach is to look for a gap in the loadings of your actual data. Like rather than saying 0.4 is really what I care about, you say, well, I've got a whole bunch here that are above 0.52, but then from 0.52 to 0.37, there's really nothing. Or maybe from 0.65, there's a bunch of stuff above 0.65, but then nothing down to 0.42. Maybe we don't want to include that 0.41, even though it's above 0.4, if everything else that's strongly loaded is above 0.65. So which variables load strongly on F1? Well, you know, regardless of whether you're going to treat 0.4 as a magic number or look for a big gap, it's going to be the same answer here. V2 is negative 0.62, V6 is negative 0.66, and V12 is 0.55, and there's nothing else all the way down to 0.32. How about F2? Which variables load strongly on that one? Well, in that case, it's V1 and V5, negative 0.7, 0.73, big gap between those, and V9, negative 0.34. So let's do a quick quiz. Which variables load strongly on F3? So which variables don't fit this scheme? Or in other words, which variables don't load strongly on any factor? You can see that we have V4, which has 0.04, 0.03, and negative 0.02, not good on any factor, and V10, 0.01, negative 0.02, and negative 0.07. What about V9? That's kind of a weird one, right? It actually has two reasonably strong loadings. It's much weaker than any of the other ones in those two factors, and it's below that magic negative 0.4 or 0.4. But it's hard really to say that this completely doesn't fit. It kind of seems to fit two of them. It's halfway in between. If the magic number is lower, V9 would be fine. So what do we want to think about V9? In fact, V9 seems to load on two factors in a moderate degree. Probably means it's actually an item that isn't really quite right for this factor scheme. So, all right, we've got our factors. How do we create scales for, say, a questionnaire? Or for saying, okay, I don't actually want to calculate across my 10,000 variables every time. I just want to know which variables to calculate across. In that case, we can actually create scales by assigning items to specific factors. So after the loading's created, you can create one factor per variable models called scales by iteratively, that's just to say, repeatedly doing this. You assign each item to one factor, and then you drop the one item that loads most poorly in its factor if it has no strong loading, and then you refit the factors. So in other words, you're going to take every single item, you're going to say every item is going to go into one factor, and only one factor, whichever one it's most strongly loaded on. And then if there are any that don't have strong loadings, you're going to take the very worst fitting one, toss it out, and refit the factors. And you'll keep doing this until every single item is in a scale and is strongly loaded. So, item selection. Some researchers recommend conducting item selection not just based on the fit to a factor, but also based on face validity. In other words, if it doesn't look like it should fit, don't include it. So for example, if you're creating a questionnaire for whether students have performance goals, and one of your items, and it loads strongly on performance goals, is, I like to eat cake, maybe you should get rid of it. This depends on how theory-driven you want to be, and how much of a theory you actually have. You know, if you really have a strong theory, if you're working on something like performance goals, which Carol Dweck and Andrew Elliott and Midgley and all these other people have been working on for 3 decades, maybe you want to be very theory-driven. But if you've got some completely new construct, maybe you don't want to be so theory-driven. What you don't want to do is feel pressured into having to have a theory and then throw things out because they don't conform with your theory that really you just kind of made up on the spot. So, okay, how does factor analysis work mathematically? How do we get these factors? Well, there are 2 algorithms. The first one is principal axis factoring, which some people rather confusingly just call factor analysis. And there's principal component analysis, PCA. Principal axis factoring fits to the shared variance between variables. It tries to find what the shared variance is, And principal component analysis fits to all variance between variables, including the variance unique to specific variables. PCA is more common these days. It really doesn't matter so much, especially as the number of variables increases. PCA is a little bit easier to compute. So how does it work mathematically? Well, the first factor tries to find a combination of variable weightings, that is those numbers you remember in that table, that best fit the data. So we're going to try to say, how can we most predict the variance in the data by finding a combination of variable weightings on the various variables. And then we take what's not fit. We take the residuals. We take the remaining unexplained variance, and the second factor tries to find a combination of variable weightings, another linear regression equation, that best fits that. So imagine you're doing a linear regression. The first step of factor analysis is just do a linear regression, and then take all the variance from that linear regression, all the unexplained variance, all the residuals, and fit a linear regression equation to fit that. And then, after you've done the second factor, take all the remaining variance, everything you haven't fit so far, all the residuals, and try to fit that with another linear regression equation. And you keep doing that until you can't fit anything more. You then make the factors orthogonal, or in other words, uncorrelated to one another. How do we do that? Well, we use a statistical process that I'm not going to go into today called factor rotation, which takes a set of factors and refits to maintain equal fit while minimizing the factor correlation. Essentially, there's going to be a large equivalence class of potential solutions, sets of, for example, 3 linear regression equations that each do an equally good job of fitting the variance. And factor rotation tries to find the solution that minimizes the correlation between the factors. So it's going to try to find factors that equally well fit all the data while fitting each other, correlating to each other as little as possible. So trying to get orthogonal, one that goes this way, one that goes this way, and one that goes this way. Looking at this another way, this approach tries to find lines, planes, and hyperplanes in the k-dimensional space where you have k variables, which best fit the data, which don't fit each other too well. And this may remind you of support vector machines. It may even remind you of spectral clustering. You can see that there are a lot of things in educational data mining where the same math, used in slightly different ways, ends up being very different things. So how do you compute the goodness of a factor analysis? Well, you look at what proportion of the variance in the original variables is explained by the factoring. This is typically computed as r squared, or the correlation squared, which in factor analysis land is often called the estimate of the communality. Once again, same thing, different terms. The only thing I'd add to this is it's usually better to use cross-validated r squared than just the original r squared on all the training data being your test data. That's still not standard. People will typically still, for factor analysis, use the test data as the training data. But if you cross-validate, you'll get a better estimate of how good your factors really are. So how many factors should you use? Well, the best approach, in my personal opinion, is to decide using cross-validated r squared. But there's an alternate approach that some people use, which is where they drop any factor that has fewer than 3 strong loadings. Now this makes sense if you're doing questionnaires. Who wants a questionnaire with a subscale with 2 items in it? Doesn't really make sense, and it doesn't give you enough data. But for other uses of factor analysis, this may make more sense. You may want factors that are outlier factors in various ways. An alternate approach is you could add factors until you get an incomprehensible factor. This is actually fairly common and fairly popular in the statistics community. You just keep going with more factors until you get a factor that you say, I have no idea what that means. Now, the only concern I have about this, and my only caution, I'm a data miner, is one person's incomprehensible factor is another person's research finding. So if you're going to throw things out just because you don't understand them, really make sure that it's really junk and not just that you don't understand it. So how much data should you have to do a factor analysis? Well, Gorsuch says at least 5 data points per variable. Cattell says at least 3 to 6 data points per variable. Gorsuch says have a minimum of 100. Comrie and Lee say, oh, well, 100 is poor. 200 is fair. 300 is good. 500 is very good. And 1,000 or more is excellent. You know, whenever you see wonderfully round numbers as guidelines, you should be just a little bit suspicious. It's probably a magic number. And as far as I can tell, these were based on Gorsuch and Cattell and Comrie and Lee's personal experience, which is good. You know, you're taking this course, you're getting my expert opinion on things. It's good to get people's expert opinion, but it's also important not to take it too seriously. If you get good things out of a factor analysis with 99 data points, or only 4 data points per variable, you know, if you get something useful, you've got something useful. If you get something that helps you think about your data, that's good. If your factor analysis leads to a better prediction model, hey, who cares? My opinion, use cross-validation, see empirically, see if it's useful. Okay, so you've done a factor analysis, You've got your scales if you want them. One more thing to do before you publish. Check your internal reliability of your scales. And people typically do this using Cronbach's alpha. Alpha is a function of the number of items, the average covariance of those items, and the average variance overall. And when you do Cronbach's alpha, it'll give you an idea of how consistent each of your factors are internally. And this is important because if you want to do a questionnaire and you have and you want to publish using your questionnaire and you don't report Cronbach's alpha, people are going to have some concerns and you may not be able to publish. It gives you an idea of not just is there a factor, but how internally consistent is your factor. So here are some magic numbers for Cronbach's alpha. I apologize for being a little flippant. Where do these things come from? They're just one person being smart and saying, I think these are good numbers, and then maybe people adopt it and maybe they don't, and then people get their papers rejected because they're slightly under a magic number that didn't matter in the first place. That said, George and Mallory say, 0.9 is excellent, 0.8 to 0.9 is good, 0.7 to 0.8 is acceptable, 0.6 to 0.7 is questionable, 0.5 to 0.6 is poor, and under 0.5 is unacceptable. So is 0.5 really unacceptable? I don't know. Depends on what you're going to use it for. Maybe you want to make sure all of your items are individually good because you don't want to waste people's time. But what's the cost benefit of adding an additional item? Maybe even though it's not all that reliable, maybe it captures part of the construct you actually care about that is part of what you want to measure. It's tricky to say. You certainly don't want things with a Cronbach's alpha of 0.0001. But is 0.49 really unacceptable? Is 0.54 not good enough for a test? It depends on how you want to use this and what you're going to use it for. If you get one thing out of this class, it should be, don't rely on magic numbers. Actually think about what you're trying to do and think about what it means. So factor analysis. It's a powerful tool for discovering unknown structure in data. It's conceptually similar to clustering, but it finds an orthogonal type of structure. Clustering finds structure and commonality within data points, the rows often in your data set, and factor analysis finds commonality and structure in your columns, in your variables. So that concludes our Structure Discovery Week. Next week, we're going to discuss discovery with models and a couple other favorite topics of mine. We're getting to the home stretch. We're getting to the really fun part. Thank you for sticking with me. I'm Ryan Baker. This is Big Data in Education. Have a good day.